Welcome to our new course on design wind loads on a medium-height building. In this course, I will explain the full and detailed process of calculating the wind pressure on structural elements and cladding and base moment resulting from these wind pressures for a medium-height office building. The assessment of wind loads for design of this structure is based on Australia and New Zealand standard AS 1170.2. However, the general concept remains the same for every other code. AS 1170 has a very detailed and comprehensive process for calculating the wind pressures. I often see people get confused with so many parameters and regulations of the code, and so I have decided to prepare this course to provide a clear roadmap for anyone who wants to learn the process step by step. I am a professional engineer working in Australia with more than 7 years of national and international experience and have a solid knowledge of Australian industry and relevant standards. I also have a PhD in structural engineering, and because of my passion for education and teaching, I have also worked as a university lecturer in the past. I am committed to provide contents that can fill the gap between academia and the industry by providing the practical courses. For this reason, I have created this course to give you the skills required to calculate design wind loads for a typical medium-height office building and make you familiar with the fundamentals of the design. My general approach in this course is to explain some basics and general concepts of wind loading on structures, and then I will explain how to calculate wind parameters in order to get the wind pressures and where in the code I'm getting these values from in a real-life example. These parameters include regional wind speed for different areas of the country, train or height multiplier, and explaining the definition of different train categories, defining importance level of the building, and return period of the wind considering the occupancy and use of the building, wind direction multiplier, hill shape and shielding multipliers, site wind speed, and finally design wind speed. I also talk about aerodynamic shape factors for different surfaces or parts of the building. Calculating aerodynamic shape factors requires calculating the external and internal pressure coefficients, area reduction factor, local pressure factor, and reduction factor due to parapet, and also action combination factor and dynamic response factor. These parameters will be calculated for windward wall, leeward wall, side walls, roof structure, and cladding surfaces with respect to two perpendicular directions of the wind. And then we can calculate net wind pressure for structural elements, and then base moment resulting from these wind pressures for the two perpendicular directions of the wind. And at the end, we will calculate the net wind pressure on claddings, which includes wall and roof elements for the two directions of the wind. This course is beneficial for structural engineering students, civil engineering students, graduate engineers, and structural engineers ranging from beginners to intermediate level who would like to refresh their knowledge and get a practical knowledge of wind loading on structures. By the end of this course, you will learn about the fundamentals and detailed process of calculating the wind pressure and base moment for structural members and cladding of a medium-height building. My goal is to add value to my students by conveying my professional and practical experience as well as explaining the theoretical concept behind the design. So please do not hesitate to ask if you have any questions through the message box here in Udemy or any other social media links which we have provided in our page. Also, you will have lifetime access to our course content, which means you will receive all the future updates and additions free of charge. Thanks for watching and hope to see you inside the course. Let's start with some basic definitions and concepts which are going to help you to understand the process of calculating the wind pressures. On the left side of this page, you can see there are some legends which are defined by Australian code or AS 1170.2. Let's look at one example here to understand these legends. If our wind is in this direction, this side of the wall is called windward wall. The other side of the wall is called leeward wall, and two other walls are called side walls. For the roof, we might have three different written legends depending on the direction of the wind and the slope of the roof. In this specific case, both sides of the roofs are called crosswind roof slope. In this example here, with the wind blowing in this direction, this side of the roof is called upwind roof slope, and the other side of the roof is called downwind roof slope. So now let's look at a very important concept about positive and negative pressures. So we want to understand, when do we call a wind pressure as a positive pressure? The fundamental is that when the wind is toward the surface or is pushing the surface, is considered as positive, and when it's away from the surface, is called negative pressure. So for example, let's look at external pressure for this building. So you can see in here, the wind is toward the surface, and then for the roof as well, on any surface around this building, if the wind is toward the surface, is considered as positive. For the internal pressure, the concept is the same, just the wind is blowing from the inside. So for example, from this side on the roof, from the rear wall. So all of these considered as positive pressures. So now let's look at the actual building. When the wind is blowing in this direction, we have a positive pressure in this direction because the wind is blowing in this way, is pushing this side. And on the other side, we are going to have suction or negative pressure, and it's because it's away from the surface. Also for the roof, we might have positive or negative pressure depending on the the slope of the roof. So here you can see the plan and elevation for this building, and it's showing the wind when it's applied in this direction for the windward wall, for the leeward wall, and for the two side walls. And as you can see, the side walls are negative because they are all away from the surface. Also, for the leeward is negative because it's away from the surface, and for the windward is positive because it's toward the surface. Let's define our building that we want to calculate the design wind load for. This building is an office building located in Sydney, and it's 50-meter high. The horizontal dimensions of this building is 25 meter by 70 meter, and the natural frequency of this building is greater than 1 Hz. The roof is flat with a 0.9 meter high parapet. Also, this building is located in a suburban train area in all directions. Our first step to measure wind actions on this building is to calculate design wind speed, or V design, and theta. Theta is shown in this picture in here, which shall be taken as the maximum cardinal direction side wind speed, or V side, and beta, which is shown in here, linearly interpolated between cardinal points within a sector plus and minus 45 degrees to the orthogonal direction being considered. So this beta is shown here, which is related to the north direction, south, east, and west directions. A conservative approach is to design the structure using the wind speed and multipliers for the worst direction. For example, if we have a building located on a hill, then it may be easily checked that the V side and beta on the exposed face would be the worst case. To simplify the design, this value could then be used as design wind speed for all directions on this building. The second step is to measure wind pressure on different sides of the building with this formula, as you can see in here. P, or wind pressure, is measured in Pascal and is a factor of rho, which is density of the air, which is 1.2 kilogram per cubic meter. V design and theta, which we have explained before. C fig, which is aerodynamic shape factor, which we are going to go to a lot of detail in the next few slides. And then C dynamic, which is dynamic response factor, which is usually 1, except where the structure is dynamically wind sensitive. This is usually the case for very tall buildings. And then we have AZ, which is tributary area for the wind. So what we need to do in here is to calculate this wind pressure on different sides of this building. For example, if the wind is applied in this direction, then we have windward pressure applied on this side of the building. Then we have leeward pressure on the rear side of the building. And then we have sidewall pressures. And finally, we have roof pressure, which we need to calculate. Each one of these pressures have their own parameters and factors that we need to calculate. Let's go through more details by looking at design wind speed parameters. The first parameter we are going to look at is the location of our building. Our building is located in Sydney, which is considered as region A. Every region in Australia has its own regional wind speed, which is based on peak gust wind data. So in Australian code, or AS 1170.2, there is a map which shows different regions for different areas in this country. And if we look at Sydney, we can see our region is region A2. Now that we know our region, we can look at table 3.1. And if we know our return period for our wind, we can get this regional wind speed. To calculate this return period, we need to do some calculations, which I'm going to explain in more detail in the next few slides. But let's assume our return period is 1000 years, and we know our region is A, so our regional wind speed would be 46 meters per second. The second parameter we want to calculate is train category. Our building is located in suburban train area. In Australian code, or AS 1170.2, there are 6 different train categories as shown in here. So train category 1, 1.5, 2, 2.5, 3, and train category 4. So if you go through the description for each terrain category, you can easily find your own terrain category. For example, if we look at one terrain category 1 as example, it says it's for very exposed open terrain with few or no obstructions and enclosed limited size water surfaces at serviceability and ultimate wind speeds in all wind regions, e.g. flat, treeless, poorly grassed plains, rivers, canals, and lakes, and enclosed bays extending less than 10 kilometers in wind directions. So this terrain category terrain category 1 requires higher wind load factor, and terrain category 4 requires lowest wind load factors. So I read this description and I have decided that my terrain category is terrain category 3 because as per description it says terrain with numerous closely spaced obstructions having height generally from 3 to 10 meter. The minimum density of obstruction shall be at least equivalent of 10 house-sized obstructions per hectare, e.g. suburban housing, light industrial estates, or dense forest. So now that I know my terrain category, I can look at table 4.1. And based on different heights and different terrain categories, we can get another factor which is called MZ and CAT, which is height or terrain multiplier to calculate our design wind pressure. So for example, if we look at our terrain category 3, and our height of the building would be 50 meter, so our factor would be 1.05. So as you can see, the taller the building gets, the higher factor we have. Also, as I explained before, if we look at terrain category 1, we will have higher factor than we look at terrain category 4. There are a few steps to calculate the regional wind speed. The first step is to determine the importance level of the building. The importance level of the structure shall be determined in accordance with its occupancy and use. If we look at table 3.1 of AS 1170.0, it explains about the consequences of failure for importance levels. For example, if we look at the low consequence of failure, this is for minor structures where there is low consequence of loss of life, or a small or moderate economic, social, or environmental consequences. This is related to importance level 1. For the ordinary consequence of failure, this is for normal structures, and for the structures where medium consequence of loss of life or considerable economic, social, or environmental consequences. So this is related to importance level 2. So the third category is where we have high consequence of failure. This can be related to major structures, which can be importance level 3, or for post-disaster structures, which can be for importance level 4. So for this category of buildings, we have high consequences of loss of human life or very great economic, social, environmental consequences. And then the last category is where we have exceptional consequence of failure. This is for exceptional structures. So this is the circumstances where reliability must be set on case-by-case basis. So now if we look at table 3.2, in this table, based on different importance level, there are some examples and descriptions which help you to determine what is your importance level. For example, the importance level number 1, so this is for the structures presenting a low degree of hazard to life or other property. So this is for the structures with a total floor area of less than 30 square meter, for farm buildings, for isolated structures, towers in rural situations, fence, mast, walls, in-ground swimming pool. So importance level 2 is for normal structures, which is not in the category of building for importance level 1, 3, or 4. For example, single family dwelling, car park buildings. And importance level 3, which has the majority of our building that we usually design, is for the structures which have where you can have more than 300 people gathered, or for daycare, primary schools, for colleges, for healthcare facilities, for airport, multi-occupancy, residential or commercial, including shops and many more examples. So our building is going to fall into this category. And then we have importance level 4, which is for structures with special post-disaster functions. So there are some examples, as you can see in here. And also there is very special structures which is going to fall into importance level 5, which is outside the scope of this code, which is Australian code. So now that we know our importance level, as mentioned, it was importance level 3, we can look at table 3.3 to determine what is our return period for our wind. So for this one, if we, so first of all, we need to know what is our design working life. Usually we have 50 years, unless we have very special structure. So in this example, we have 50 years design working life, and our importance level is 3. So if we look at the wind case, the annual probability of exceedance would be 1 over 1000. This means our return period is 1000. So also this table gives more information about other events. So if we have a snow, then the return period would be 250. And if it's earthquake, then the return period would be 1000. And if we want to look at serviceability limited state, then our return period would be 25 years. So now we have all the required information to calculate our regional wind speed. We just need to look at table 3.1 with 1000 year return period for our wind, and region A. We know that our regional wind speed is 46 meters per second. The other factor we need to calculate is wind direction multiplier, or MD. So if we look at table 3.2, for different region, you can see, and for different cardinal direction, we can get different factors. So what we usually do, we look at the this option, any direction. If you want to go for these 8 different cardinal directions, it's going to be a very time-consuming process. So we take the value of 1 for MD. The parameter related to the topography is called MH. And in our case, because the ground slope is less than 1 in 20 in all direction, this factor would be 1. But as you can see in table 4.4, the more slope that we have, the higher factor we will have for this parameter. L and H are shown in figure 4.4 and 4.3 for the hill or for escarpment. H is height of the hill, and LU is the horizontal distance from the top of the hill to the location that we have half of the H from the top of the hill. Similarly, it's shown for escarpment here as well. Terrain or height multiplier, or MZCAT, can be taken from table 4.1 from AS 1170.2. This factor is for all regions. So based on our terrain category, which is terrain category 3, and height of the building, which in our case is 50 meter, we can get the factor of 1.07 for MZCAT. For intermediate values of height and terrain category, we can do linear interpolation. The other factor is shielding multiplier, or MS. For this reason, we can look at table 4.3. And as you can see, there is a shielding parameter in here, which depends on number and spacing of shielding buildings around our building and height of our structure. Because in our case there is no other building of greater height in any direction, we can take the value of 1 for MS. Otherwise, we need to calculate these shielding parameters, but alternatively, we can be a little conservative and take the value of 1 as well. Again, we can have linear interpolation for intermediate value of S. Now that we have all the parameters to calculate V site and beta, we can use this formula and calculate our design wind speed. So our regional wind speed was 46, MD was 1, MZ and CAT was 1.07, and MS and MT were 1. So our V site wind speed is 49.2, and our design wind speed, referring to my previous explanations, is the same as site wind speed for all directions, which is again 49.2 meters per second. The other very important parameter in calculating wind pressure is Cφ, which is aerodynamic shape factor and has to be determined for a specific surface or part of the surface. For calculating pressure, the sign of Cφ indicates the direction of the wind pressure on the surface. Positive value means pressure acting towards the surface, and negative value means pressure acting away from the surface or suction. And then finally, the wind action effects used for the design would be the combination of internal and external pressures on the building. For enclosed building, we have two different Cφ that we need to calculate. The first one is Cφ and E, which is for external pressure, and the second one is Cφ and I, which is for internal pressures. As you can see, the formulas are a little different. Cφ and E has 5 different parameters, and Cφ and I has 2 different parameters. We are going to go into more detail for each one of these parameters in the next few slides, but let's look at CPE to start. So CPE is external pressure coefficient, and we need to look at table 5.2 from AS 1170.2 to get the value of this CP and E. This CP and E depends on the height of the building, and if the roof of the building doesn't have any slope or is near zero, as shown in this picture, the height would be shown as height of the building. And if we have the roof with a slope, then the average roof height would be our H. So now that we know the value of our H, we will go to table 5.2. And if the height of our building is more than 25 meters, then this value would be 0.8. And if the height of our building is less than 25 meters, for buildings located on ground, when wind speed varies with height, then this value would be 0.8. When wind speed is taken as taken for Z equal to H, then this value would be 0.7. For elevated buildings, this value would be 0.8. So in our case, because the height of our building is 50 meters, our CPE would be 0.8. For the leeward walls, I need to look at two different directions for wind loading. I'm calling these two different directions as wind 1 and wind 2 in this picture. So looking at wind 1, it means wind is normal to 70-meter wall. So I need to look at table 5.2b to determine CPE factor. So for the wind direction of 0 and the roof shape of hip or glaive, as you can see, we only have two options, hip or glaive. And for the roof pitch or alpha of 0, our case is 0, so it's less than 10. This alpha is shown in this picture. So now we need to know what is the value of D over B. So let's look at the definition of D and B first. So if the wind is blowing in this direction, the dimension that is perpendicular to the wind is B, and the parallel dimension of the building is called D. So for this wind 1 direction, D over B would be 25 divided by 70, which is 0.35, which is less than 1 as per this table. And this means our CPE would be negative 0.5. For the other direction, which is wind 2, D over B with the same definition would be 70 divided by 25, which is 2.8. Now, if I go back to the table, the D divided by B is divided between these two values of 2 and 4. So I can do linear interpolation and get a value between negative 0.3 and negative 0.2. But conservatively, I can take the value of negative 0.3. So if I look at the side wall for determining this CPE, I need to look at table 5.2c. So as you can see, for different values of horizontal distance from windward edge, which is defined as 0 to 1h, 1h to 2h, 2h to 3h, and more than 3h, we have 4 different values for CPE. So if I look at, for example, wind 2, what is this table is saying is that between 0 and 1h from windward wall, so the wind is blowing in this direction. So from here to 1h, it says our wind would be negative 0.65, and between 1h and 2h, our wind load would be a little less, and the factor would be negative 0.5. But we always have to be careful because the wind is not gonna be only in one direction. It would be in both directions. So in the other case, if we look at the other direction, then we will have the bigger load in this side and then less load on the end part. So for this reason, I'm going to take the bigger value, which is negative 0.65 for the side wall. For the roof structure, we need to look at table 5.3a. There are two more tables in AS 1170.2 which are related to upwind and downwind slopes and also for alpha larger than 10 degrees. As you can see in here, CPE depends on H over D and horizontal distance from windward edge of the roof. So again, let's look at two directions of wind and define our CPEs. So if we look at wind 1, our H would be 50 and D is 25 as explained in the previous slide. So H divided by D would be 2. And if we go back to our table, so our H over T is more than 1. So we need to take the value of negative 1.3. In this special case, because half h is 25, which is equal to our d, we have only one CPE in this direction. If we look at the other direction, which is wind 2, our h over d would be 50 divided by 70, which is 0.7. Now we can see 0.7 is between this 0.5 and 1. So we need to do interpolation between the values from these two columns. For 0 to 0.5 h, we need to do the interpolation between negative 0.9 and negative 1.3, which is going to be negative 1.06. Between 0.5 h to 1 h, which is 25 to 50 meter from the windward edge, we need to do interpolation between negative 0.9 and negative 0.7, which is going to be negative 0.82. And between 1h, which is 50, to the end of the wall, then we need to do interpolation between negative 0.5 and negative 0.7, which is going to be negative 0.8. So what does this value means? So if the wind blows in this direction, we have the maximum, the bigger value of CPE in this area, and then we have a smaller value, which is 0.82 in here, and then we have a smaller value in this area, which is 0.58. But as explained in the previous slide, if we have the wind blows in this way as well, which we always have, then we will have the maximum value in here, and then we have the same 0.82 in here, and then we have a smaller value in here. So we need to always be careful because we have the wind blowing in two directions. Now we want to calculate CPI, or internal pressure coefficient. For this reason, we need to look at table 5.1a. So depending on the permeability and the wind direction, we might have different values for CPI. For example, if we have only one wall permeable and other was impermeable, there would be two situations. If the windward wall is permeable, as shown in here, then CPI is equal to CPE for the windward wall. If the windward is impermeable, like you can see in here, then CPI would be negative 0.3. If two or three walls permeable and other walls impermeable, then if the windward wall is permeable, which are these three situations, then the CPI would be either negative 0.1 or 0.2. And if the windward is impermeable, which are these examples, these three situations in here, would be negative 0.3. If we have all the walls permeable, then the value of CPI would be negative 0.3 or 0, whichever is more severe for combined forces. And our case is because it's air conditioned, we can consider it effectively sealed. So our CPI would be either negative 0.2 or 0, whichever is more severe for combined forces. So when we say combined forces, means combination of internal and external wind pressures. So just to remind you again, for the direction of internal pressure on the inside the building, if you look at this picture that you have seen in the earlier slides as well, so where we say positive value, it means the wind is blowing toward the surface. So as you can see, three examples for the roof, for the wall, and for the rear wall.